Welcome back. When we left off, we were talking about BCS theory, and in particular, we had solved the Cooper problem. We discovered that for arbitrarily weak interactions, two electrons above the Fermi surface will form a bound state to lower their energy. And this suggested that once, if you have a Fermi surface, two electrons will jump above the Fermi surface, form a bound state, lower their energy, and then two more will jump above the Fermi surface, form a bound state, lower their energy, and so forth, and the whole Fermi surface becomes unstable. And this calculation by Cooper around 1956 really broke open the research into the direction of superconductivity. So in 1956, lots of people, both in the West and also in the Soviet Union, were working on the problem of superconductivity. Many of the greatest minds of the century, people like Landau and Feynman, were all hot on the trail. And Bardeen was lucky enough to have hired Cooper and also to come work with him as a postdoc, and also I was lucky to have a very brilliant graduate student named Bob Schrieffer. Anyway, right in the middle of this, as they're trying to figure out, how is it that you're going to make a theory of superconductivity based on this picture of Cooper pairs, Bardeen had to stop his research because he had to go to Sweden to collect his Nobel Prize. The Nobel Prize for the transistor. He'll win another Nobel Prize for superconductivity. There's a story that when he got there, he actually didn't come with his entire family because some of his kids were in college. He didn't want to interrupt their studies, and the King of Sweden said, why didn't you bring your whole family? And he said, well, I'll bring the whole family for my next Nobel Prize. And then when he won his next Nobel Prize, he did bring his whole family. Anyway, he didn't have a solution yet, but he was pretty confident that they were going to come up with something. While he was gone in Sweden collecting his Nobel Prize, it was actually Schrieffer, the graduate student, who had the brilliant insight. He was off at a conference in New York, and in a break in the conference, he was on the New York City subway and had an aha moment. Really, all of a sudden understood, this is how I'm going to solve the problem. And he went back to Urbana and talked to Cooper, and they just started work on this immediately. And Bardeen comes back from Stockholm. Within a few months, they had the entire modern theory of superconductivity completely nailed shut. Schrieffer's PhD thesis has got to be one of the best PhD theses ever. If you ever get a chance to look it up and pull it out of the library, it's almost identical to his book on superconductivity, which is a modern classic of the field. I guess there were other incredible PhD theses, like de Broglie's PhD thesis, which was, but that was way back in 1924 when people didn't know anything, and he had, I think it was like a 20-page thesis where he, proposed the idea of de Broglie waves. That was a pretty good PhD thesis too, but since de Broglie's PhD thesis, Schrieffer's PhD thesis has got to be one of the best, one of the most pivotal moments of the century. Anyway, what was it that Schrieffer realized? Well, he did base a lot of what he was doing on the idea of Bose-Einstein condensation. So let's back up for a second to remember what we did for bosons. So for bosons, recall we can write an operator which creates a boson in an orbital phi. I guess we'll write it like this: phi of r, psi dagger hat of r, like this, and this creates a boson in this orbital. And then if we want to make a BEC, we just occupy, put n such bosons in the system, starting with the vacuum, and we just create n times. Now the question is, can we do something similar for pairs of fermions? So now we're going to switch to pairs of fermions, fermion pairs. So let's define a operator. We'll call it a twiddle dagger, and we'll write it as integral dr1, integral dr2, some pairing shape of the pair wave function in g of r1 minus R2, psi dagger R1 up, psi dagger R2 down. Again, as we had in the Cooper problem, this boson is in a there's no reference to R1 plus R2. There's only a reference to R1 minus R2. So this is putting the boson in the boson center of mass in the k equals 0 orbital. So if you think the pair center of mass has k equals 0. We can write this in more standard second quantized notation as a sum over k, g sub k, c dagger k up, c dagger minus k down, and where g sub k here is the Fourier transform of this g of r. In simple cases, we can take again, move myself out of the way. We can take the g of r here to be real. So let's assume this is real here. In which case, we'll need g of k equals g of minus k, as we did for the Cooper problem, and also for a symmetric pair. If the orbital of the pair wave function is rotationally symmetric, we can take g to be a function of the absolute value of k only. That's a simplification. It's not absolutely necessary. Okay, so this is creating this creates a pair, a singlet pair, in 1 up down 2 minus down 1 up 2 g of r1 minus r2. Okay, so it creates a singlet pair. Either way, whether you want to write it in Fourier space or in real space, that's what this a twiddle operator does. Now the question, is a twiddle a boson? Well, how would we know if it's a boson? Well, it would be a boson if it satisfies the bosonic commutations. A twiddle, oops, I'm putting twiddles below. I guess I used the convention twiddles are below. A twiddle dagger equals 1. In fact, it would be good enough if a twiddle dagger were some constant, some number. We don't care what the number is because we could just change our definition, multiply the a twiddle dagger by the square root of that 1 over the square root of that constant, and then we'd have the right commutation. So any constant is okay. Any constant would be okay. So let's actually check if this is true. So we'll use this definition of a twiddle dagger. Oops, a twiddle dagger. Twiddle under. Dagger equals that thing. So if we take the commutation a twiddle dagger, we get sum over k prime, g k prime star, g k, and then we have the commutator g minus k prime up, g k prime down, g k dagger, k up. Sorry, c. These are c's, not g's. Like this. That's just plugging in this definition into this commutator, and with just a little bit of commutation, we can derive that this gives us sum over k gk squared 1 minus n hat number operator k up minus number operator minus k down. So it's not a constant, it's an operator. So this thing is an operator, and that means these a twiddle operators are not bosons. They are, you might say they're almost bosons if the right-hand side is going to be roughly constant. And it might be roughly constant because we know that the ground state of our system is going to be pretty close to a Fermi sea. And so maybe, if you don't change the Fermi sea too dramatically, then the right-hand side, if you take its expectation, it's not going to change. It's not going to change that much. So you can say, well, maybe these a twiddles are pretty close to commuting and giving you a constant, but they're, strictly speaking, they're operators. They're not the right-hand side is an operator, not a constant, so these things are not really bosons. We might call them quasi-bosons or pseudo-bosons or something like that. But they're not real bosons. But the strategy is to pretend they're bosons. So let's pretend they're bosons for a second and try to create a BEC. Can we make a BEC in quotes of these pseudo-bosons of A twiddle daggers? Can we do this? Well, we can. We can make a wave function here. This is made of 2n fermions, which would be n pairs, and we can write that as A twiddle dagger to the n on the vacuum. You can evaluate what this wave function looks like. It is, sometimes it's described as being the so-called Pfaffian of G of R1 minus R2, or maybe call it G of 1, comma 2, position 1, position and spin 1 of position particle 1, position and spin of particle 2. And what that means is it's an anti-symmetrized product of G, the pairing function of particles 1 and 2, times the pairing function of particles 3 and 4, times the pairing function of 5 and 6, so forth and so on. Okay, so what does this mean? So just an example of what this Pfaffian means, if I wrote anti-symmetrized product of G1, 2, G3, 4, what I mean is that this thing up to an overall constant, which is a definition of what I mean by anti-symmetrized, this thing will be G1, 2, G3, 4 minus G1, 3, G2, 4 plus G1, 4, G2, 3. So let's see, did I get all the combinations? 1, 2, 3, 4, 1, 3, 2, 4, 1, 4, 2, 3. I think those are all the combinations, and they come with a minus sign each time you make an exchange, because so that you have something with fermionic symmetry. So this actually turns out to be, this is really the fixed number form, fixed n, or 2n, form of the BCS wave function. And it's nice to be able to write this thing down, but it's essentially completely useless for doing any sort of calculations. It's awful to try to do any calculation with a wave function that looks like this terribly complicated sum. So that's not so good, although it's nice to have written it down. So what do? Well, we recall for a second that we could write a BEC as a coherent state. So remember, if I want to write a BEC as a coherent state, I could write it as e to the alpha a dagger and some orbital on 0, and the expectation of the number of particles is alpha squared. Well, we can do the same thing here for our pseudobosons, and we will write our BCS wave function, BCS, as e to the alpha a twiddle dagger, where each e twiddle creates a pair on 0. And let's write out what we mean by that e to the alpha a twiddle dagger here. This thing, what we mean is e to the alpha, and I'm writing out the definition that we had before. So gk, c dagger k up, c dagger minus k down on 0. So I just put in upstairs what we had for the definition of a twiddle upstairs here. And now I have e to the to a sum. I can of course write that as a product of exponential of a sum is a product of an exponential, and that's okay to do because a pair of fermionic operators will commute through a pair of different fermionic operators. So you get two anti-commutations, so you get a plus sign. So it's okay to write this as a product over k of e to the alpha gk, c dagger k up, c dagger minus k down. on 0. And then we should notice that this operator, sometimes this operator here, it's convenient to call this, maybe we'll do this later on, maybe we won't, I don't know. Sometimes people call this thing P dagger K. It creates a pair of oh my gosh, I didn't mean to do that. A pair of fermions here with K and minus K in a singlet state, like this, with a K spin up and minus K spin down. I'll call that a pair creation operator. And the thing to notice is that the square of this operator is 0. P dagger. Let me write it out. P dagger K squared. That's C dagger K up, C dagger minus K down squared is 0 because this would involve putting 2 fermions in the same orbital, which you can't do. So that means if we take this expression here and multiply out the exponent, expand the an exponential, we can expand the exponential series. We have the usual 1 plus alpha gk, c is product over k, c dagger k up, c dagger minus k down. And you might say, well, okay, we need the quadratic term plus dot 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 here, alpha squared over 2 factorial dot dot dot, and so forth. But the next term and all terms thereafter vanishes because it would involve the square of this operator, the C dagger C operator. And when you square it, you get 0. So you can truncate the series here. Stop the series right there, and that applied to 0. So this is our BCS wave function in this rather nice form. Now, one thing to notice about it is, like our coherent state representation of our BEC, the BCS wave function here has an indefinite number of particles in it. There will be this term creates no particles, this term creates 2 particles, and so when you multiply out this whole series, you have a superposition of all number of particles up to a very, very large number of all possible k's. But like BEC, there is some expectation of the number of particles, which will be finite. Also, like the coherent state, we have the problem that the wave function is not normalized, not equal to 1, and that is annoying. It's always nice to work with normalized wave functions. So let's actually calculate what the normalization is, and then we'll divide through by the normalization to make everything simpler. Although you do see sometimes the BCS wave function written in this form, it's more usual to see it written in a normalized form. So let's write this out. Psi BCS equals 0 product of k 1 plus alpha star g this is k prime gk prime star c minus k down c k prime up, and then product of k 1 plus alpha gk c dagger k up c dagger minus k down, all on 0. Okay. So sorry that's sort of running off the edge there. Okay, so how do we evaluate this this product? Well, it's useful to think about every k mode separately, and each k mode basically is independent of each other k mode. So we can write that as a product of k, and we'll write this as 0 in the state k. So there's 0 in k and 0 in k with spin up and 0 in minus k with spin down. That's what I mean by the vacuum of k. Then I'll have 1 plus alpha star gk c minus k spin down, c k spin up, and then 1 plus alpha GK, oops, alpha star, this GK also has a star, GK, C dagger, K up, C dagger minus K down on 0 in the K state. So you start with 0 in the state with 0 in K up and minus K down, and then you can create them or not, depending on whether you're hit by this term or this term, and then you can annihilate them or not, depending on whether you're hit by this term or this term. Well, okay, the only way you get something non-zero for this term is if you create the pair and then destroy the pair, or if you don't create and then don't destroy. The cross terms will vanish because there'll be there's no overlap of this with the vacuum, and there's nothing to destroy here. So so we get the BCS normalization is then product over K of 1 plus alpha squared GK, GK inside squared, GK squared, like that. Okay. Now, what's then conventional is we want to divide our BCS wave function through by this normalization. And the way we do it is we define parameters called U and V, always called U and V in the literature. UK is 1 over square root of 1 plus alpha squared GK squared, and then VK is alpha GK divided by square root of 1 plus alpha squared GK squared. Okay, so alpha GK is just VK over UK. All these K's are vectors, although the dependence, as if we have a, so this product here is product over all K vectors. The dependence of GK may only depend on the magnitude of K if we're thinking about a rotationally symmetric system and a rotationally symmetric pairing, which often we have. And we have the nice condition that UK squared plus VK squared is normalized to 1. So then I can rewrite the BCS wave function, just dividing through by this normalizing factor everywhere for product of all K's, that this then becomes, we'll look back way back here at what the BCS wave function was. Up here is this guy, way up here. And then I'm going to divide through by these denominator terms, square root of these things, such that I can write the BCS wave function in its normalized form as product over K, UK plus VK, C dagger, K up, C dagger minus K down on 0, where the UKs and the VKs satisfy this normalization condition. This is a 1 sitting here. 1. 1 in black. 1. 1. 1. I see what's going on. 1. That's 1. Okay. And this is the form of the BCS wave function. This. And it's we're going to use it an awful lot. Okay? It's the way you usually see it in the literature, and this is normalized such that psi BCS equals 1. Okay? Okay, so what we have is we have a trial wave function. What we don't know is what these coefficients we want to find out. We want to know what the U's and V's are, or equivalently, we would like to know what the G sub K's are, or equivalently, what we want to know is what is G of R1 minus R2. What is the pairing wave function? What is the shape of, you put the two fermions together to make a pair. What's the shape of that pair? What's the shape of that wave function? And to determine that, we need actually to have a Hamiltonian. Use a Hamiltonian. And we want to, and the scheme is to take this BCS form as a variational wave function, and we want to minimize the energy of the Hamiltonian with this as a variational wave function. The usual variational strategy is you have some form for your wave function, and you just vary your parameters until you get the lowest possible energy, and that gives you your estimate of the ground state. Okay, so we have to write down a Hamiltonian. Okay, what's our Hamiltonian? Well, the actual Hamiltonian, which we're probably interested in, is going to look like sum over k and sigma, epsilon k sigma minus mu, c dagger k sigma c k sigma. So actually what I'm writing here is I'm actually writing h minus mu n, mu times the number of particles in the system. It's actually, it's quite important to keep track of the chemical potential, because we're going to be working with wave functions that have an indefinite number of particles, and so you want to make sure that that the addition of a particle gives you the right amount of energy, so you have to keep track of the chemical potential as well. So the Hamiltonian, this is the non-interacting part, the usual part, and then we have our usual, well, we wrote it as sum over A, B, C, D, V, A, B, C, D, C dagger A, C dagger B, C, D, C, C, I guess. And what we usually want this thing to represent is some sort of integral dr prime, rho of r, v of r minus r prime, rho of r prime. Some sort of interaction, some attractive interaction between our fermions. And strictly speaking, what we're actually doing is we start with a model which has electrons and phonons in it. We, quote, integrate out the phonons, and we get an effective interaction, a low energy interaction for the electrons, and we approximate the attraction between the electrons as something of this simple form, just a pure attraction, and we're going to work with that. So this Hamiltonian is too hard. It's too hard to work with, and typically what we do is we sort of follow Cooper's lead, and we write a grossly simplified form of the Hamiltonian. So let me write down the so-called BCS Hamiltonian, HBCS, which, okay, so the non-interacting part remains simple, k sigma, epsilon k sigma minus mu. So epsilon is just the usual, p squared, and this is the usual kinetic energy. And this combination here, epsilon minus mu, epsilon k sigma minus mu, is sometimes written as psi sub k. It's not a function of sigma, I guess, so we get rid of the subscript sigma, epsilon of k. So get rid of that subscript sigma. Epsilon k, so we can write this thing as psi if we want. Psi sub k, c dagger k sigma, c k sigma. So that's the non-interacting term. And then the interaction term is going to take a very special form, sum over k prime, v k prime. So this v doesn't have 4 indices like we had up here. It has only 2. And the c daggers and c's are of a very special form, c dagger k up, c dagger minus k down, and c minus k prime down, c k prime up. Okay, so what is this form doing? This is annihilating a pair, and this is creating a pair. So let me rewrite this as our pk prime, our pair annihilation operator, and this is our pair creation operator, pk dagger. So what this is doing, it's oh, and I should actually also add one more thing. We have to assume that k and k prime both close to the Fermi surface, to EF, to Fermi surface. In particular, we want it to be within h bar omega Debye, because we know that that the attraction mediated by phonons is only operative if the energy of the electrons is within omega Debye of the Fermi surface. Okay, so what is this form of the interaction doing? What is it actually describing? So let me draw a Fermi surface here. So here is a Fermi surface. See if I can draw it round. Okay, that's oblong. See if I can draw it round. That's round. Okay, here's our Fermi surface, and it's filled with particles. And then we are going to take a fermion at position K up, and another fermion at position minus K down, and well, I guess the way I've actually drawn this is, let's make these primes, K prime up and K prime down, and they're going to scatter. It's going to destroy a pair with K prime up and minus K prime down, and it's going to create a pair at some other momenta called K up and minus K down. So it's going to be something that moves a pair somewhere around the Fermi surface, like this. Okay, so it scatters a pair into another pair. Okay, so one more comment, that we want to assume V K K prime equals V K prime K, which just says we have a sort of symmetric scattering, and so that's going to imply that V is real somehow, that the scattering is real, and we also want to assume it's attractive, weak and attractive, and it should only be operative if K and K prime are both close to the Fermi surface. Now, if we compare this form of the interaction to the actual form of the interaction up here, they look quite different. So this, these things don't have to be paired. They don't have to be at K and minus K. They can be, two of the same spin. They can be two of different spins. And this is really very special. It's only annihilating two that are directly opposite each other with opposite spins, forming a singlet, and this one similarly is only creating a pair with opposite spins and opposite momenta. So why is this okay? Well, one, it's a huge simplification, but it gets the right physics. It gives the right physics, and that's a good reason to use it. It is justified much later in history. It was justified by renormalization group calculation. RG justifies. If you know anything about a renormalization group, you can think about flows of interactions, and this sort of scattering of a pair is the only relevant perturbation of a Fermi surface. So this is what remains when you sort of scale to the lowest possible energies and the lowest and the longest wavelengths. That's something I'm not going to derive, but it turns out to be true. Okay, so with this gross simplification of our Hamiltonian, we then want to calculate E is psi BCS, our BCS Hamiltonian, psi BCS, and we want to minimize the energy over our variational parameters. Minimize over UK and VK subject to our normalization condition, UK squared plus VK squared equals 1. Okay, so to do this, we're going to need a couple of expectations. We're going to need to calculate things like what is C dagger K up, CK up in the BCS wave function. Well, okay, what's that going to look like? Let's see if I can, let me put another line here so I don't run out of space. So that will be 0 in the k state, and then there'll be a uk star plus vk star, c minus k down, ck up, and then the thing I'm actually trying to calculate is c dagger k up, c k up, and then uk plus vk c dagger k up, c minus k down on 0 in the k state. Okay, so what is this expectation? Well, the only way you get if you multiply this out, you get a whole bunch of terms. If you got hit by the u, then you're going to get 0. This number operator is going to measure 0 fermions in the k state. If you're hit by the v, you're going to measure a fermion in the k state because you just created one. And then in order to get back to the ground state, you have to choose this term again to annihilate that pair that you created over here and get back to the ground state. So this expectation is going to be vk squared. Okay, and similarly for if I did the same calculation with the downspins, it would be the same answer. We're also going to need these so-called anomalous correlators, c dagger k up, c dagger minus k down, or we can think of that as the expectation of the pair creation operator, and maybe we'll use a little bit of shorthand replacing the pair creation operator. pk dagger is c dagger k up, c dagger minus k down. So this thing is going to be 0 in the k state, u star k plus v star k pk. Thing I'm measuring is p dagger k, and then I have a uk plus vk p dagger k on 0. This just saves me writing a lot of c's. So how does this thing become non-zero? Well, if I create a p dagger, if I create a pair here, I try to create another pair here, I can't. It's trying to create two fermions in the same state. So this term is going to vanish. Draw that. This term vanishes. And what else vanishes? Okay, and if I create this pair here, I then have to get rid of the pair to get back to the ground state. So that means, I guess, this term vanishes also. And so what I'm left with is equals v, oops, make this in black, always good to choose the right color. Amazing what you can learn by just writing neatly. So Duncan Haldane is famous for saying when he did some of his work on topological properties of one-dimensional Luttinger systems, which is part of what he won the Nobel Prize for. He's quoted as saying, "It's amazing what you can learn by just being careful." And he says what he did is he did the calculation everyone else was doing. He was just a little bit more careful. Okay. Okay. Anyway, we also are going to need an analogous calculation. So C prime down, C K prime up, and that's going to be U star, just the same calculation, or the conjugate of the same calculation, U K prime star V K prime. Okay, so then let's, so we have these correlators that we just calculated, and let's let's copy our BCS Hamiltonian here. Here we go. Copy this. Copy and find its expectation in the BCS state. Paste. So there's our Hamiltonian, and the energy. Energy. Don't need these. Okay. The energy is going to be, well, from the first term, we're going to get, so this thing is called psi, sum over k, and psi k, and the expectation of the number operator we decided was just vk squared. And then you get a factor of 2 because there's two spins. They're supposed to sum over spins, and this result is independent of the spin state, so I get a factor of 2 there. And then we'll have sum over k and k prime, and we want the expectation of C dagger, and the expectation of CC in the two different states. So this will give us V k prime, VK star UK, U star K prime, VK prime. Okay? So now we have the energy of this energy is equal to the expectation of H BCS in the BCS wave function state. Now we have to figure out how to minimize this energy over the possible values of these U's and K's, which are variational parameter. Okay, so we're going to make a couple of simplifications, which actually these aren't crucial, but we'll assume a real wave function. I think I mentioned this before. Wave function, real pairing wave function, and also rotationally symmetric. And that means G is a function of absolute K only. As I've been drawing, I've been saying GK. I haven't been drawing vectors just out of laziness. And this comes from G of R equals G of minus R. So the fact is, okay, good. And let's see. Yeah, I guess we'll need that. Yeah, I guess I'm going to need that. Actually, maybe I'm not going to need that. Get rid of it. So this allows us to assume, we can assume that UK and VK are both real, remembering that GK is alpha GK was VK over UK. I can just take them all to be real. Choose the phase of alpha to also be real. And we also have this normalization condition, VK squared plus UK squared is 1. And so, okay, if I have two things which squared both add up to 1, it sort of makes sense to let VK equal cosine theta k and UK equals sine theta k. Okay? This is a sensible thing to do. And then we can plug these U's and V's into our expression for the energy that we just derived up here. So doing that, we get the energy, expectation of the Hamiltonian in the BCS state, is then sum over K to psi sub K. That's the kinetic energy measured with respect to the chemical potential. VK squared here is then cosine theta K squared. Cosine squared theta k. It's kind of interesting that you notate that with cosine squared theta k instead of being forced to put brackets. All right, whatever. Notation that we all use and we don't even think about anymore. Okay, and then we have sum over k and k prime. We have v, k, and k prime, and then we have a u and a v at k and a u and a v at k prime, and we're assuming these are real. So this is going to give me a, I guess, a sine of theta k, cosine theta k, sine theta k prime, cosine theta k prime. Well, there we go. Sine times cosine we recognize as sine 2 theta. So this is sine 2 theta k divided by 2. Let's try to draw that a little bit better so you can see it. So this is sine 2 theta k divided by 2, and this is sine 2 theta k prime divided by 2. And we can also take cosine squared here and write that as 1 plus cosine 2 theta k divided by 2. A little bit of trigonometry comes in handy here if you don't remember it. Okay, so now the v's and the u's are no longer variational parameters, but the thetas are our variational parameters, and we would like to minimize the energy over all these thetas. So how do we do that? Well, we'll take dE d theta q equals 0, and what does that equation give us? Okay, we have 0 equals, from differentiating with respect to this theta, we get, I guess, minus 2 psi sub q times sine of 2 theta q, and then a 2 cancels the 2 in the denominator. And then we'll have plus cosine 2 theta q, that's from differentiating with respect to one of them, times the sum on k, v q k, sine 2 theta k here. Now here we, you might, if you're counting factors of 2, you might think that we lost a factor of 2 downstairs here, but we didn't, because what we did was we assumed vkk prime equals vk prime k, and we had to take the derivative with respect to both the first factor and the second factor, and so that gave us twice as many terms as we otherwise would have had if we just differentiated with respect to one of them. And so this is the correct expression. Okay, and then we can simplify this thing a little bit more, giving us a rather important equation, just moving this to the other side and then dividing through by psi. We get that the tangent of 2 theta q equals, right this way, 1 over psi q, 1/2 sum on k, v qk sine 2 theta k, this, and this thing, quantity here in brackets, I'm going to define this quantity in brackets to be called delta sub q, equal, so this whole thing here, I'm going to define this whole thing in brackets to be minus delta sub q, so this whole thing here will be written as minus delta sub q over psi sub q. This delta sub q is known as the gap function. Delta q is known as the gap function, and we've defined it with a minus sign because it's we expect delta to be overall positive. Delta will be overall positive. This entire term should be overall negative because we expect V to be we want V to be an attractive interaction if we're going to make pairing, and so this whole thing in brackets is going to come out negative. So we'll define this as minus q. Now the reason this is called a gap function is because it's going to turn out that this gap function is related to the gap in low energy excitations of the system. The system with superconductor is not going to have any low energy excitations in agreement with Landau's criterion for superfluidity. You shouldn't be able to create quasiparticles, and this is going to be the gap in energy around the Fermi surface where there's no excitations. Since this is a rather important equation, maybe I'll circle this one as well. We're going to use it again a number of times, and it's worth sort of unpacking the definition of this delta a little bit more. Trying to remember what it is with this sine 2 theta represented. If we back up a little bit, we remember that sine 2 theta came from sine theta cosine theta, and the sine theta cosine theta came from a vk uk. So if we back up a couple steps, we can define this gap function, delta of q, is minus sum over k, v qk, uq star vk, uk star vk. Okay, and if you remember where we got the uk vk from, we got that from an expectation of one of these anomalous correlators. So this thing will also be written as sum of vk vqk of c minus k down, c k up. Okay. Good. So this gap function is also going to be some sort of order parameter for our superconductor. And like in Bose condensation, this order parameter is, like, recall that in BEC, I'll make a little region over here where we recall BEC, we had an order parameter expectation of psi dagger, or maybe we could have used expectation of psi, but a number non-conserving order parameter. And you'll recall that there were some people, Tony Leggett in particular, who objected to the use of a number non-conserving order parameter, and we found that there are ways to work around that number non-conserving order parameter if you need to, but it's a lot easier to work with a number non-conserving order parameter. And that's what we're going to do here. This delta is defined as a number non-conserving order parameter, but if we really needed to, we could find a way to write a version of it which has a fixed particle number by maybe considering the correlator of a pair creation and a pair annihilation operator, where maybe the creation and the annihilation are far from each other or something like that. Okay, so backing up, we still have this gap equation here. Tangent of 2 theta q is going to give this minus gap divided by psi q, and what we want to do is we want to somehow solve for the appropriate thetas here. So to do this, we need more trig identities. So more trig. So we're going to need 1 plus tan squared of 2 theta equals secant squared of 2 theta. So if we squared this side, we're going to get our tan squared, and that's going to enable us to write from this identity is going to enable us to write the cosine of 2 theta q. That's, remember, cosine is 1 over secant, so this is going to be plus or minus 1 over the square root of 1 plus tan squared of 2 theta. And similarly, sine of 2 theta q is going to then be, well, the tangent times this thing, so it'll be plus or minus tangent of 2 theta over the square root of 1 plus tan squared 2 theta. And here we go back and recall that tan squared 2 theta, the tan of 2 theta is this minus delta q divided by psi q. So then this thing can be rewritten as minus psi q over the square root of psi q squared plus delta q squared. And this one can be written as delta q over the same square root, psi q squared plus delta q squared. So here I had to choose either the plus or the minus root here. It actually doesn't matter which one you choose. You can choose either the plus or minus root, but it has to be done consistently such that the ratio of the sine divided by the cosine gives you the tangent, and you get exactly one minus sign, because the tangent of 2 theta better be minus delta q divided by psi q. Okay, so we've chosen the signs consistently such that this is true. A little bit of complication with the choosing the sign of the square root. Okay, so we're almost there now. We can now plug this back in to our gap equation. Let's actually rewrite the gap equation as tangent of 2 theta equals minus delta q over psi q. So we then have we're going to now we plug it back into this expression here, their definition of delta q. So remember that the definition, let's actually just copy this, use this. This is the definition of delta q. Paste. Okay, so delta Q equals minus delta Q equals, okay, delta Q equals minus this, equals minus that thing. And we now know what sine 2 theta is because we just calculated it here. So let's plug that in, and we get delta Q equals minus 1/2 sum over k v q k delta k over square root of delta k squared plus psi k. Oops, delta k squared plus delta k squared. Okay, did I get that right? Yeah, delta k squared, like that. Okay, so this is also a very important equation. It is known as the BCS gap equation, and the solution of this allows you to figure out what this gap function delta is. It's very, very general for singlet superconductors. It does not have to be the case that you have a nice symmetric wave function. It doesn't have to be real. If it's not real, you have some absolute values floating around, like this thing has absolute values on it here. But I'll take this off because we're assuming delta is real here. And so the wave function doesn't have to be rotationally symmetric, and in fact, it doesn't even have to be a singlet superconductor. But it's pretty similar even for triplet superconductors, with which there are very few in the world. But this equation is always in BCS theory what you end up somehow solving. To solve it, we then have to choose a form for our interaction. Form for interaction. And again, we're going to use the intuition. It's going to look very similar to what Cooper did with the Cooper problem. We're going to take VQK in the following form. It's minus V naught if the energy of Q and the energy of K measured from the Fermi surface is less than h bar omega Debye. And remember, the attraction due to phonons is only active if the fermions are low energy excitations. If the and psi here is the energy measured with respect to the Fermi surface. So low energy excitations above the Fermi surface are attractive, and higher energy ones are not. So we just call it zero otherwise. And then my claim is that this gap equation is satisfied. Gap equation satisfied by the following form. Delta Q equals just delta, constant, scalar, for psi Q less than equal to h bar omega Debye, and zero otherwise. Okay? And to check that, we just take the, let me make this a little smaller so you can see them all. So what we do is we just plug this form into here and plug this form into all the deltas, and then we can also cancel a factor of delta here and here. There'll be a delta scalar because delta of Q is being replaced by delta, so there'll be a delta scalar here and a delta scalar here, which can cancel out, and the gap equation can be simplified to the following form. Write it here. It'll be 1 equals V naught over 2 sum over K 1 over square root of psi K squared plus delta squared. And we've lost the minus sign because V naught here is defined with a minus sign. Okay, so this is now also an important equation. This is a simplified form of the BCS gap equation for this simplified interaction, and this equation can be solved for the value of the delta, which tells you how big the region around the Fermi surface is where there are no excitations. So we can go further than this, which is to do what we usually do. We replace sums over k's with a density of states. So the sum over k is going to become an integral. Well, density of states So we'll assume the density of states doesn't vary too much around the Fermi surface. So it becomes a density of states at EF. And this density of states, I'm going to define this density of states to be the density of states for one spin species. One spin species. I think that's the correct way to do it. Integral d epsilon, and then it will go from the chemical potential minus the Debye frequency to the chemical potential plus the Debye frequency, because we're only going to be summing over k's which are close enough to the Fermi surface. So actually, I guess we should have actually written this here to make it correct. So psi k has to be less than h bar omega Debye in that sum. Okay, so we're replacing this sum, this restricted sum, with an integral over energy states around the Fermi surface. And so we get 1 equals, I guess, 1/2. There's a V naught density of states for one spin species around the Fermi surface. Then we'll write this as from minus h bar omega Debye to h bar omega Debye integral d psi 1 over the square root of psi squared plus delta squared. And this integral, if you're good with your hypergeometric functions, not hypergeometric, hyperbolic trigonometric functions, this thing is an arc sinh. So this thing becomes V naught density of states the Fermi surface for one spin species, arc sinh of h bar omega Debye divided by delta. And we can invert this equation to get sinh of V naught, of 1 over V naught density of states of the Fermi surface equals h bar omega Debye over delta. And we know that for small V naught, for V naught small, the argument inside the sinh is large, and so the sinh becomes nothing more than an exponential. And so in particular, we get delta equals 2 h bar omega Debye e to the minus 1 over V naught density of states of the Fermi surface. Extremely similar form to what we got in the case of the Cooper problem, where we found again that we have this non-analytic form. This is non-perturbative in the value of V naught, that any order in perturbation theory will not predict this because it has zero radius of convergence, and it's crucial that there's a density of states of the Fermi surface, otherwise there's no gap function. So there's lots we can calculate further than this, and there's one that's assigned for homework, which I won't do here. It's not too hard. If you calculate the Hamiltonian, the expectation of the Hamiltonian with the BCS wave function minus the Hamiltonian of the Fermi sea, let's call it in the normal phase, this thing is how we define the condensation energy. I guess times volume if you do it for a big system. Condensation energy per unit volume. Let's just call it the condensation energy of the whole system. Back equals condensation energy for the whole system. If you do the calculation correctly, you will get the energy is 1/2 density of states of the Fermi surface, gap squared, I guess, times the volume of the system. And you'll recall when we were doing London theory, from thermodynamics, we also found that was mu naught h critical squared divided by 2 times the volume of the system. So that makes a connection between the gap function and the critical field, the gap function and the condensation energy. So this is a homework assignment. It's not too hard. We know how to calculate the expectation value of the BCS Hamiltonian because we just did things like that, and we just subtract from it the energy in the normal state of the same Hamiltonian. So what does this BCS wave function look like? Well, let's back up. We're going to use back way up to here. we're going to need, sorry about this scrolling, I know this pain, way back, where is it? Oops, way too far. Yeah, okay. We're going to need the U, way back here. Yeah, back here. Sorry, I know. Okay, so U and V are cosine theta, and V and U are cosine theta and sine theta. So let's see if we can evaluate those. Scrolling down. So if we plot UK squared, that's sine squared of theta k, and sine squared of theta k is 1 minus cosine 2 theta k divided by 2, and we actually calculated cosine 2 theta k. We needed it back up here. Where was it? We calculated it here. Okay, so we know what cosine 2 theta k was, so let's plug it in. So this thing is then equal to 1/2 1 plus psi k over the square root of psi k squared plus delta squared. I guess it would be delta k squared if it was here. Delta is just a constant. And then vk squared is, well, we can make it 1 minus uk squared if we want. And that will be 1/2 1 minus psi k divided by the square root of psi k squared plus delta squared. Okay, so what does this look like if we plot it? Let's plot this. So, oops, try again. Okay, so this is energy, and maybe here is the chemical potential, and here is, make this 1, and let's draw this across here. Okay, that's 1. And so Vk below the Fermi surface, okay, so Vk below the Fermi surface, psi k is, if you go to very, very large k, which is negative, this thing becomes -1, and then this whole factor becomes 1 plus 1 divided by 2, or it's going to become 1. But above the Fermi surface, this becomes positive. This factor will become 1, and these two will vanish. So we'll get something that looks kind of like this. It will be 1 down here, it will be 0 up here, and somehow goes between in the middle. Okay, so this is Vk. Whereas UK does exactly the opposite. It starts at 0, and then saturates to 1, UK, like this. Okay, so it looks, and recall what the Fermi function, what these things are. That these things are UK plus Vk c dagger k up, c dagger minus k down on 0. So this kind of looks like the Fermi function. That if you're below the Fermi surface, you're definitely filled. That every k that's really far below the Fermi surface is definitely filled. And if you're really far above the Fermi surface, UK, you're definitely empty. The V's drop to 0 if you're way above the Fermi surface. And then in between, that it sort of crosses over slowly between definitely filled if you're very far below the Fermi surface and definitely empty if you're very far above the Fermi surface. This distance over which it changes is on the order of delta in energy, or several delta. So it looks kind of like a Fermi function with a spread or temperature, which is about delta, but it's not a Fermi function. And the key difference here is that a Fermi function converges to 1 and 0 exponentially as you go far from the chemical potential, whereas these functions actually only converge algebraically. So it's not exactly a Fermi function, but it's sort of morally similar. So we can use some of these results actually to answer one of the questions that we started with, is how is this not like a BEC? And to answer that question, we want to ask, how big is a pair? Roughly, what is the size of one of these pairing wave functions? We'll recall that GK is the Fourier transform of G of r minus r prime, this pairing wave function. And this thing is well, it's alpha vk over uk, and it varies non-trivially, oh my gosh, come back, varies non-trivially, for I guess when you're within about delta, within delta of the Fermi surface. So maybe it's less than or equal to delta, maybe 2 delta or couple delta or something like that. So if you're in this range here, then the u's and v's are varying, or the g of k is varying in this range, and outside this range, the g is the u's and v's are, sorry, this is not vk, this is vf, v Fermi. So the energy, this thing is psi sub k, okay? The difference in energy from the chemical potential. So that means that delta k is on the order of the gap function, the gap value, divided by the Fermi velocity, to say Fermi energy is Fermi velocity, which Fourier transforming means that the change, basically the length scale associated with in position of the binding function in position is Fermi velocity divided by the gap, and this quantity here is known as the pair correlation length, which gives you roughly the size of a pair in the system. Now, this pair correlation length, which is also uses a symbol psi, is not too different from the coherence length that we calculated in Ginzburg-Landau theory. So to find the relationship, let's go back to, let's see, where was it? Here, where we found that the condensation energy can be written in terms of both the gap function here or in terms of HC. So here I'm gonna be really swift here. I'm gonna drop factors of mu naught h bar e 2 pi square root of 2. Lots of factors like that are going to be dropped, but hopefully it'll be enough to give you the idea. So the condensation energy from BCS theory we found is the gap function divided by times the density of states of the Fermi surface. Okay, and the gap function we just derived here can be written as the gap parameter, I guess I should call it, as VF divided by psi pair. Okay, and that thing gets squared. The density of states of the Fermi surface, well, that's proportional to the particle density divided by the Fermi energy. And we can simplify this more, knowing that mv squared, mvf squared, mass times vf squared is more or less the Fermi energy. So vf squared divided by ef is basically 1 over the mass. So this whole thing is going to be 1 over psi pair squared times n divided by m. Okay. On the other hand, we also said that this thing is mu naught hc squared, and if you recall what from Ginzburg-Landau theory, that hc was basically the magnetic field that you would find if you had a box with one flux quantum in it, and remember, flux quantum is made up of factors of h bar and e, and so that we can say a flux quantum has value 1, if we're being simplified here. And if our box has a distance scale on one side of lambda and psi, the coherence length, on the other side, so dropping a bunch of factors, this thing is basically 1 over psi coherence length, the Ginzburg-Landau coherence length squared times lambda squared. And what was lambda? Lambda squared, it was lambda squared was the mass. I guess there was an energy, the energy squared, superfluid density, and there was a mu naught, which I'm going to drop also. So the right-hand side here, this right-hand side becomes 1 over psi coherence length squared, and then let's see, it's 1 over the superfluid density divided by the mass. So at low temperature, this means that the pair wavelength, the pair length scale and the coherence length are basically the same. But as you get close to the critical temperature, the superfluid density and the electron density no longer match each other. And well, okay, over here, recall that okay, anyway, so the superfluid density and the electron density no longer match each other, so the pair length scale and the coherence length are actually going to differ from each other close to the critical temperature, but at low temperatures they tend to be almost exactly the same. And the important thing here to realize is that psi, this coherence length or this pair correlation length, is typically much bigger, or often can be much bigger than the spacing between electrons. In your conventional superconductors, this will be the case, and this is the sense in which your BCS superconductors are very different from Bose-condensate. Remember that if the pairing was extremely tight, if they were bound extremely closely together, that could happen if the binding energy was extremely high, greater than the Fermi energy. Then you can think of these as sort of point bosons, and the point bosons would go around and condense as a BEC, the way that any boson condenses. But in BCS theory, you have the possibility that the coherence length can be much longer than the distance between electrons, and yet you can write this wave function that effectively pairs the electrons into things that kind of look like bosons, and still makes this a superconducting condensate. Before ending for the day, let's see. Yeah, maybe before ending for the day, maybe I'll say 2 more comments. First comment about BCS theory. First, what about non-isotropic interactions? You can have non-isotropic interactions. And a classic case of this is high TC superconductors, perovskite high TC, which again there have been a million papers trying to figure out. While the mechanism of high TC is subject to debate, there are some things that people agree about, and what people do tend to agree about is that a nice model of this is to start with a planar lattice, square lattice, so like this, and the parent compound is a antiferromagnetic insulator. So we'll have upspin, downspin, upspin, downspin, so forth and so on. Okay, and then you add a few holes to the system. Upspin, downspin, upspin. The holes run around and sort of melts the order. It sort of ruins the long-range antiferromagnetic order of the system. But nonetheless, there is a tendency due to this antiferromagnetism for spins to neighbor spins, spins anti-align. Okay. Now, if you think about one site here, and then it has neighbor sites here, 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 here. If this spin on this site is up, it can form a nice pair with some guy here, because this guy on this neighboring spin is going to be down. That's antiferromagnetism. Its neighbors are going to want to be down. So it can form, if it wants, it can form a pair like this if it wanted to. But if you look on the diagonal up here, the diagonal on this site here is going to be up. And these two spins are going to be aligned, and you can't form a pair with two aligned spins. At least you can't form a singlet pair with two aligned spins. So you have good pairing in x and y direction, but bad pairing, bad along diagonals. So how do you describe that? Well, G is no longer the G that we used before. When we wrote G as a function of K, that's rotationally symmetric. Sometimes it's called S-wave pairing. And we don't want that anymore. Here we want G to be a function of R as a vector, or R1 minus R2 as a vector. R1 minus R2 is a vector, which will imply G is a function of K as a vector. And in particular, we want to have the shape of the orbital look like good pairing in these directions and bad pairing in these directions. Okay, so if you think about the shape of the wave function, it will sort of look something like this. Now, if you think about your atomic chemistry for a second, this looks like a d orbital. If you give these lobes plus amplitude and these lobes minus amplitude, then this looks like a d orbital. This looks like d wave pairing, which you can think of as, so this one is, as S wave is angular momentum L equals 0. This one will be angular momentum L equals 2. And if you have angular momentum L equals 2 here, it very naturally has to have nodes between the positive lobes and the negative lobes of your atomic orbital. The model one would use for this is that your VQK is of the form, so minus V naught cosine 2 theta Q, cosine 2 theta K, and the solution of the BCS equation will be delta cosine 2 theta Q, and we call that D wave. So this is a lot of the sort of interesting modern superconductors have this property that the pairing wave function is not rotationally symmetric, but has some atomic structure to it, some microscopic atomic structure to it. The other comment I'm going to make is about the possibility of triplet superconductors. And these are very rare superconductors, although a few are known. And a simple example of a triplet superconductor is just to imagine all the spins in the system are spin polarized. So spin polarized fermions. So they don't have a spin degree of freedom, or just declare all the spins are pointing up. We can write a BCS wave function in the form, exactly a similar form, UK plus VK, C dagger K up, C dagger minus K up on 0. The order parameter, we're going to have C dagger K up, C dagger minus K up is going to be non-zero. And that will, by fermionic symmetry, this thing is going to be, if we commute these two operators through each other, this thing is going to be minus C dagger minus K up, C dagger K up, which means we have to have delta of K equals minus delta of minus K. So delta is going to have some structure in K space similar to this, but with where the sign changes as you change the direction of K by inverting it. So again, there's some examples of this. For example, of this would be the case of a p-wave orbital. So the p-wave orbital would look like like this, where this is a positive lobe and this is a negative lobe, and you can again remember that from your atomic chemistry. So VKQ and minus V naught cosine theta Q cosine theta K, and because this because this changes sign as you change the direction of k, as you invert the direction of k, this is appropriate only for triplet superconductors, and this will have a solution. Delta Q is delta naught cosine theta Q, like this. These triplet superconductors, although they're very rare in nature, they do exist. BCS theory, or we believe they exist, BCS theory more or less holds up with very few changes. Oh, this is called P wave. With very few changes, just a little bit of bookkeeping, keeping track of spins now pointing in the same direction instead of spins pointing the other direction. But these triplet superconductors are actually quite interesting, and I think probably I'll do the last lecture of this series. We'll discuss some of the properties of triplet superconductors which make them particularly interesting. Okay, in the next lecture, we'll finish up BCS theory, discussing its excitation spectrum, some of its properties, and Josephson effect. Okay.